Well, welcome everybody. Thank you for taking the time to be here and to listen to my spiel here. And thank you, Randy, for the invite. As Randy mentioned, my name's Sean Mulholland. I am the regional sales manager for Mitsubishi Electric. I've been with Mitsubishi going on 5.5 years now. Was essentially born into the industry. My family had a family-owned and operated HVAC business in San Antonio, where I grew up. I currently now reside in the Houston, Texas market, but I do cover a sales team that covers all of New Mexico, West Texas, South Texas, and East Texas. So, just a little bit about myself. Grew up in the industry. I've done a lot inside of, if you can imagine, an HVAC kid growing up in their own family business. I've done everything from installation to marketing to essentially having a senior partner managing position. But dad wanted to retire. I had better options elsewhere. So it's been a very good, great 5 years with Mitsubishi here. Previously, I was in distribution. I did work for Train Technologies for about 3 or 4 years before I came to this side. So just to get started with some of the stuff here today, what I'll be sharing with you all is here's sort of a brief summary or agenda of what I would like to cover. So I want to give you some history background as to heat pumps in general. When did they start? When was it mainstream? When did they start coming super popular? We'll start off with that, and then kind of what is a heat pump. So if you're not super familiar with the inner workings of what a heat pump is and does and how it's different from other uh, major markets disruptors. Kind of go through that at a very high level, some of the different technology features. How do we actually measure its efficiency compared to other items on the market? Features and benefits both in residential and commercial. So I'm going to try to touch on some of the different reasons as to why we're seeing some of the things we're seeing in the residential trend side, and then also on the commercial side. Now, I will say I am not a super commercial expert. We do have a commercial team. I am more so on the residential side. However, I know probably just enough to be dangerous on the commercial side as well. We'll go into some cost comparisons and what things to look out for when it comes to looking at comparing cost, best practices while utilizing heat pumps. So what are some of the things that you have to watch out for when it comes to selecting the proper equipment, making sure it fits the needs of the space, and then the industry changes that we are currently going through. So to get started, just a brief timeline as far as some of the HVAC history. So it really started to take off air conditioning wise in the 1960s. So in the 60s, there was a lot of involvement with heating elements. So we knew how to heat a home in the 1960s, but really when it came to air conditioning in a home, it became mainstream in the 1960s. So heat pumps enter the market in 1960s, very early technology. Not people didn't quite understand how they worked, how to work on them. So very early technology in the 60s. Fast forward to the 70s, there was a 70s oil crisis. That really gave us the chance, or at least the heat pump side, a chance to really push forward with research and development when it comes to the investment side of things. So a lot of research and development money was spent in the 70s due to the oil crisis into heat pumps, into more efficient ways to heat and cool really any type of space, whether if it was commercial, multifamily, residential, office buildings, things of that nature. But in the 1990s, this is where we really start seeing a step forward or a leap forward into some of the Department of Energy side with the regulatory and setting some minimums for HVAC products. So 1990s was kind of the 10-year gap of really starting to pick up momentum with the heat pump side now that there is some efficiency minimums that are tied to the manufacturer to hit. And then fast forward into the 2000s, When it's Mitsubishi specific, Japan, we introduced our first inverter driven compressors into the US market. So the early 2000s was a good, exciting time for the Mitsubishi end. Then, as you know, the last 5 or 8 years, the HVAC industry in general has probably changed more so than in the last 10 or 15 years with the refrigerant change, the M1 new test standards, the ASHRAE stand. I mean, there's all different types of standards being elevated that manufacturers have to hit or have to target. So that's just a little bit of history as far as, when did it actually heat pumps become mainstream? And the one thing that I really want to make clear, if it's, one thing that you take away from this presentation is that not all heat pumps are equal. Not all heat pumps are made the same. Not all heat pumps are researched and developed to hit and attain certain target measures. So I want to really emphasize that as we go through this presentation, I am making a case not just for our technology as Mitsubishi or Metis, but heat pumps in general. And how I'm going to treat my audience is an audience that, if you were looking for a heat pump for your own home or your parents' house, I would want you to know this information moving forward uh, to make an educated decision on what you would like to have in your own home, or even if you're out there specing commercial spaces or even high-end residential homes, this is a product that you would want to use. So one thing that I want to highlight here is in that 90s to 2000s range is where heat pumps in general really got a bad reputation. So this is kind of a section I'd like to call your grandfather's heat pump. Now, if we remember back in the 90s, that's when the minimum efficiencies that manufacturers had to hit. So again, very early technology, not a ton of research and development as in the early 2000s, late 2000s. But in that time frame, a lot of these heat pumps were what we call entry level. So they weren't inverter. They didn't have the type of compressors that are in them today. They were primarily designed for your milder climates, so anything pretty much below the Mason-Dixon line. They also required electric heat strips. So they did not have the heating performance or cold climate performance as they do today. So I'll kind of hit on some of these other things as we move through this presentation. And back in the early 90s, a lot of companies that are still around today were first generation, second generation owned. So a lot of companies went through this period of trying out new technology and heat pumps. And they might have been in colder climates. They might have been in slightly less milder climates than you see in the South or Southeast. And this is where heat pumps got a bad rap. This is where you saw a 40 to 50 degree performance decline. And what I mean by that is, if you were to set one of these older style heat pumps in Ohio or Cincinnati or New York, a lot of times when it came to 40 degrees outside, you would start seeing a big performance decrease in heat pumps. So a lot of these companies experienced that. And so this was a hurdle that we had to get over going into, the 2010s, the 2015s. He had limited control options and again, very early technology. As we fast forward to today, we're experiencing full inverter compressors. And what I mean by that, it's not your single stage, your dual stage, energy hungry compressors. Just like with every other segment of industry, we also go through technological updates and advances. I think the one, metaphor I can make or simile is, look at the automobile industry. A lot of times when you get into a car now, there's a lot more tech in that car than there used to be 10 or 15 years ago. Same thing with HVAC is there's a lot more tech going into the HVAC manufacturing standards or baseline product, that there is a much better performance increase going into the 2020s and the 2025s of the world. Flash injection technology, I'll speak on this when it comes to cold climate readiness. Advanced control options. So now we have the ability to control things from an ecosystem standard of our mobile devices or apps, and everything exceeds UL code and is 33 SEER and above on some options. And then we have our coefficient of performances have done nothing but increase over the last 10 to 15 years. So now we've kind of seen this shift of, heat pumps weren't necessarily the greatest back in the early 90s or early 2000s. And when the DOE standards started to push more and push more and push more to do better, whether if it was during refrigerant transitions or when we talk about grid resiliency and demand response, we start seeing a lot of companies invest in this technology, and it's just grown double percentages year over year since 2008. When your typical unitary brands like the Trane and Carriers and the Lennox of the world only grow single digits, whether if that's in market share or if that's in total revenue, they grow single digits. A lot of the heat pump sides grow double digits year over year since 2008. So not your grandfather's heat pump anymore. And the one thing I'd like to make clear here is that just like with every other industry, our industry has also gone through a lot of technological advances. So busting some myths that, heat pumps aren't made for cold climate. It's just false. You have a lot of case studies out there. There are a ton of market share data to actually debunk this. And so I think when we look at some of the technology side, hopefully it'll become more apparent that these things can work almost just about anywhere. And when we look at the different types of heat pumps that we'll kind of go through is, the first one is there is a air source style heat pump, which is a majority of what the residential side of Mitsubishi really goes in towards. So kind of how a heat pump works is the very top here. So if you are in a colder climate, all you're essentially doing is you're utilizing the outdoor coil to transfer heat to inside. And then when you're going into your summer months, all you're doing is you are rejecting heat on your outdoor coil and exuberating the colder on the inside. So when you look at how this is actually done is, when you look at heat transfer of your indoor and outdoor units, all it is just a reverse swap. So your reversing valve is your key component in a heat pump, which allows us to effectively do that. So your traditional heat pumps work very similar. However, they rely on electric resistance heat. So if you're familiar with, what one of these may or may not look like, there's a picture of one there on the top left-hand side. This is where heat pumps in the early 90s and 2000s had a hurdle to cross, because every traditional heat pump that was being installed in that time frame had electric resistance heat. So when the economic balance point of that heat pump was, okay, let's say if it was 40 or 30 degrees outside, and my heat pump back then wasn't able to keep up with the demand for heat inside the house, that's when the electric heat strip would kick in. So, and there are still traditional heat pumps out there that are being manufactured that require electric resistance heat kits. So when you look at a traditional heat pump, just know that Mitsubishi doesn't really fall inside of that category. But when you look at some of the major brands that are out there that don't have quite the performance or the technology or the compressors backing it, this is what they are referring to as a traditional heat pump with electric resistance heat. So this is where a lot of the energy consumption goes into a heat pump. That's, a traditional one. So electric heat kit will come on. Typically, an electric heat kit is anywhere from 10 to 15 kilowatts, which requires anywhere from a 40 to 50 amp breaker on the inside of the house, not not including the 40 to 50 or 60 amp breaker that's required for the outdoor unit. So a lot of energy consumption potentially here, especially when you are at your winter peak loads. So dual fuel is a technology that allows us to continue to use gas or natural gas inside of our homes while utilizing the benefits of a heat pump. So, for an example, our dual fuel option is, you can keep your existing furnace. Typically, a furnace inside of a residential space or even a commercial space at that will last longer than your fan coil will, or your coil in general. So a lot of times, residentially speaking, customers will keep their furnace, and then we're able to bolt on our coil to that, which is going to be the heat pump side of things. So with this speaking here is if you have somebody who really doesn't necessarily want to get rid of gas, we can bolt on the dual fuel option. Then we have a back end app that will actually show that homeowner at what point in time their balance point is switching from gas to electric, or heat pump in that sense. So, over a period of time, when you go through your different winter peak loads, you can actually see when your system is using gas or when your system is actually using your electric side or your heat pump side. And what we find more times often than not is we'll have a customer go through a complete year or two of having a dual fuel system, and they're noticing that their gas bill is almost zero during the winter time, because the heat pump, when matched with our P series outdoor unit and our hyperheat matchups, is you're getting 100% heating capacity at -10 degrees. So your gas is almost not needed at that point in time. The fourth one on here is geothermal. So geothermal is definitely probably the most expensive way to heat and cool a house or a residential space or a commercial space at that. To give you kind of an idea of what geothermal actually does, is it actually uses the ground below or adjacent to the structure to heat and cool the space. So in a more mild or southern environment, this may look like a home that's next to, I know this is very popular, like in the Lake Travis area of Austin. If you're next to a lake, you can do an underground loop of coil, which will take the energy or cool energy from the lake itself and then take that coldness and basically disperse it into the house. And it runs almost in reverse when you want to heat the house. So it's really utilizing the earth beneath the structure to heat or cool the space. Most people will tell you that it's probably the most energy efficient way, but it's also the most expensive way to really gain that edgewise in on the efficiency side of what a heat pump can or can't do. And finally, the air to water, which is becoming more and more of a topic of discussion, especially in Europe. There's a lot of air to water in Europe, and all this essentially is you're using that side discharge outdoor unit, and now you're able to heat and cool your house utilizing water source. So you can essentially run it to a hydro box, which will feed your tankless water heater or your tank water heater, and then it'll provide hot water to any type of radiated floor, fan coil, hot water. Same thing with on the cool water side. So this is going to be more of a trend, I think, moving forward, especially when we look at the new Department of Energy standards for GWP, which is global warming potential of refrigerant. So this is already something that's being heavily utilized in the EU, which The EU typically on the HVAC side is anywhere from 8 to 10 years ahead of the US. So the EU has already been using R32 refrigerant for probably 10 plus years. They've been using the A2L stuff, and now they're transitioning more air to water. So more to come on this topic. The other topic that I kind of want to discuss is the technology functions and features that you will see on almost all, if not the entire product line that Mitsubishi has. The way that I like to break this down is, there are some body parts, quote unquote, to a heat pump. And the best way that I can describe this for someone who is trying to kind of puzzle piece this all together is first you have your heart. This is your compressor. The compressor is the heart that pumps the refrigerant through the system. And there's two main styles of compressors we use, rotary and scroll. Your scroll type compressors are typically larger and your rotary type are typically smaller. What I mean by that is the amount of refrigerant that can flow in and out of the compressor. So your rotary type is going to be more on the residential side. Your scroll type is also residentially focused, but it can handle larger tonnages, 3, 4, and 5 tons, 6, 8, and 10 ton three phase. You're going to see larger scroll type compressors on those systems. Your rotary type, you're going to see on multi-zone, single zone, 3 to 4 tons or below. So think of the compressor as your heart. Your heart valve is this four-way valve that we've been discussing. The four-way valve is kind of that main artery coming out of your heart, and it's sending your blood either in reverse or in forward motion. So think of the four-way valve as your heart valve, and then your blood vessels are your electronic expansion valves. So these are going to be what regulates the refrigerant going into an indoor system. And I can throttle that up and I can throttle that down. You have large blood vessels and you have small blood vessels. So this is kind of how I like to explain some of the technology pieces, is that you have to have these three key body parts in order to have a functioning heat pump. And then when we talk about cold climate, our H2I or Hyperheat series is proprietary technology to Mitsubishi. And this is where we come into the flash injection side of the compressor. And when we talk about flash injection, all I really want you to imagine is when you look at a traditional air conditioning unit or a traditional heat pump, will ramp a compressor up to about 60 hertz. 60 hertz meaning, it's pumping out as much as it can when it comes to the heating side of things. 60 hertz is really the limit. Our flash injection technology bumps that 60 hertz to 120, so almost doubling its performance when it comes to the heating side output of the heat pump. So when we look at these three different levels of hyperheat, these are the three different SKUs or layers of hyperheat that Mitsubishi offers. So the first one being 100% heating at 5, and the last one here being 100% heating at -13. And what I mean by that is if you have, a 4-ton unit on your house and it's -13 degrees outside, that system is going to give you 48,000 BTUs of heating at -13. You are not losing any performance capacity out of that unit when it comes to the colder climate side. So this is a technology that Mitsubishi has been working on probably over the last 15 years and perfecting more and more and more. And we can only expect, as the technology increases or more research and development is made, we can potentially see that -13. I think our next target is -18. Not a lot of areas in the country are at -18 for very long, but we do have parts where that particular performance is needed. Now you can enhance the performance by adding wind baffles, hail guards, but more so on the wind baffle side, you can get an extra couple degrees of performance when you're adding wind baffles to some of these pieces of equipment. Another piece of technology is, the way that we can zone our systems. So multi-zone, particularly speaking, is you can have a house that is attached to a multi-zone system, meaning that you can have anywhere from 2 to 8 zones on a house, and have those different zones in the house either on or off or within a couple degrees of each other. So where the benefits that this kicks in is, take a home like this where maybe it might be an upstairs and downstairs scenario. Maybe you're not using the upstairs as often as you're using downstairs. You can completely turn the upstairs off if you wanted to and just run the downstairs. Typically in a residential environment, it's not simultaneously heating and cooling. It's either you're all in cooling or you're all in heating. So this gives you the opportunity to fluctuate where you want your house to be heated or cooled at different times of the day. So comfort zoning is been a real big push when it comes to the residential side of the retrofit business. So if a homeowner is not satisfied with their 10, 15-year-old system and they wish they could utilize a certain room more and not have the rest of the house heating or cooling, this is where the different zones comes into play. A couple of other different pieces of technology that we have is, you're going to see on the top left-hand side that we have what's called our 3D IC sensor. The 3D IC sensor, there's 2 or 3 different levels of it. On the residential side, it's really meant just to track where your heating or your heat load is coming from. So, if I'm in my office right now, and if I put one of these above my head, that 3D IC sensor is going to sense that there is a heat source in the room, and I can either send air directly or indirectly to that space. Now, where that starts to evolve in the commercial side of things is that we do have a version of 3D IC sensor where it does the occupancy setback. So when we talk about the IECC code and having the demand response controls, we are really set up for that when it comes to the commercial side. The dual barrier coating on the top right-hand side is a coating that we came out with a couple of years ago because we understand that these systems do and will get dirty, and it can become a maintenance nightmare to keep them clean. So we said, well, our passive way of approaching this is, why don't we just clean the unit as it runs? And so there's really it's minimally invasive to take a unit apart, clean it, and move on with your life. But the dual barrier coating gives us an extra edge in when it comes to keeping the unit cleaner for longer periods of time, which reduces the maintenance cost or overall cost of ownership, in years to come. Our comfort app is our residential focused app that you can download, and we do have Wi-Fi on board some of our high wall systems now, but we also have Wi-Fi options for every system that we have out there. So you can potentially remotely log in and access your home comfort from wherever you are, as long as you have internet or a Wi-Fi connection. And then the other thing that we have to deal with in the South is humidity. Now, humidity could be a vice or it could be a virtue. Now, up in the West Texas area, New Mexico area, it's very dry. I'm a person who actually likes their humidity. I don't like it when, my nose gets real dry or my skin gets real dry. I actually prefer my humidity. So I like my southern climate. But we have ways to combat either or. So we have ways that, our smart dry mode works in potential in climates where it's, not so dry or it's on the coast. So we have things and we have technology that's implemented to help overcome different variables in different markets. Whether if you're in a cold climate market, we have hyperheat. If you're in a humid environment, we have dry mode. If you are somebody who likes tech and wants to access their home comfort system from your phone, we have that type of technology available. So kind of wrapping up the technology side and moving into the energy The energy efficiency management side of this is now we're kind of dialing into how does this actually correlate with grid resiliency, demand response. And the one thing that we have to understand is fundamentally how does the heat pump work? On the left hand side is your conventional system. Okay, now this is probably 60 or 70% of homes that have this type of technology in them. And the way I don't want you to look at this is like a light switch. So on your conventional systems, and you could probably walk outside of your house today and hear a neighbor's system kick on. I know I can. And when that system kicks on, it's drawing 60 amps right there. So that compressor is drawing 60 amps of power from the grid to continuously run at a 72-degree set point. So the unit comes on, goes off when it reaches set point, comes on when there's a temperature swing, and so on and so forth. And it does this all day, every day. Essentially, here in the South, I mean, I think on average, looking at my home energy report, my system will run probably anywhere from 9 to 12 hours a day, just given the ups and downs of the peak season of the year. Now, if we're at like a heat index of 115, which it can get here, my system's probably running upwards of 18 hours a day to try to keep up with a 74, 75-degree set point inside. But when we look at the Mitsubishi systems, so on the right-hand side here is what I want you to look at this is like the gas pedal of a car. When you need more acceleration, you are either somebody who likes to smash the pedal, or you're somebody who is getting, on the highway at a slower rate of acceleration. But we're not just turning on and off a light switch. Inverters are meant to run 24/7. Now they do shut off when it reaches set point, but the algorithm behind how it reaches set point is much different than from a single stage or a dual stage system. And what I mean by a single stage system is that a compressor that is single stage has one speed. It's on or it's off. It's pulling the 60 amps, it's drawing the 60 amps until it reaches set point, and then it turns off. That's the picture on the left. Two stage compressors essentially we'll do it in two different stages. So in your first stage, that compressor will run up to 70% of its capacity. And if it's still not reaching set point, then that compressor kicks on into second stage, which will kick it on to that 60 amps, and then it'll ramp back down into first stage, and then essentially shut off when it reaches set point. When we talk about inverters are completely different in the algorithm in which we reach set point. So in order to reach our set point, we are going to continuously monitor the influx of air coming into a return, and then we will measure the delta between what we want the temperature at and what the temperature coming in is at. And then we are going to run efficiently and effectively to, over time, hit that set point. Now, we can ramp up if we are far away from set point. If we are somewhat close to set point, we can ramp down. But when you look at the amperage consumption of what a single stage does versus an inverter, when that inverter first kicks on, it'll probably draw, less than 9 amps of power and consistently draw less than 9 amps over time, depending on the set point. So when we talk about energy consumption on this side, is that we go about it in a different way that is, it's less harmful to the system, because a system is only going to continuously run as long as that compressor is working. So if we're continuously drawing 60 amps on startup, it's going to burn that compressor out eventually, right? That's what those compressors are made for, though. Our inverter style compressors, whether rotary or scroll, they're not made for that. They are made for the continuous power coming into there, regulating it, and then determining where we need to be on set point. So that's the way I kind of want you to envision your more energy efficient systems versus your less energy efficient systems is the power consumption on startup, and then the algorithm behind actually obtaining set point. When we look at the CEE tiers, this is something new that went into effect, I believe, last year of January 1. So all the CEE tiers are trying to do here is delegate in which tier is going to be most efficient for manufacturers, but also your different climate zones. So different climate zones will call for different tier levels. So this is going to be something that is going to be ever changing. So the CEU Tier 1 going forward in January 1 really only changes your capacity ratio. So the capacity ratio has increased, meaning that manufacturers will be targeted to get more out of their systems at that 47-degree temperature split. So this is going to be something that is ever changing in our industry. They're going to continue moving the goalpost further out when it comes to how we utilize HVAC and incentivize homeowners or even commercial developers or people in that realm of real estate to move forward with better technologies that consume less energy. When we look at a heat pump's economic balance point, okay, so the balance point is when is it smart for a heat pump to know when to not be a heat pump anymore? So this really comes into play with dual fuel systems. But in order to understand what COP actually is, it's going to be the measure of its efficiency or performance. So how you can measure that is at the bottom here, it says a heat pump with a COP of 4 as an example. It'll provide 4 units of heat for every 1 unit of electricity used. So 1 unit of electricity could essentially be 1 kilowatt of power, which equates to 3,400 BTUs of heat. There's a lot of math involved there, but to make this easier to understand is if you look at the chart, and I believe this is a 3-ton ducted unit on the Mitsubishi side. It's probably hyperheat. So when we're listing out our COPs, this is really where the rubber meets the road because we're comparing our system to a resistance heat system and comparing the overall output or energy efficiency between those two systems. So if I'm looking at a COP at 47 degrees, so that's in degrees, you see 17, 5, -5, and -13, is at 47 degrees, my heat pump is 4.68 COP larger than your resistance heat. So what that means is it's 400 times more efficient than your output of your electric heat kit. So as you keep going down that COP line and that COP at -13, I'm still almost 200 times more efficient than your resistance heat at that point in time at -13. That's how you are measuring where your rubber meets the road on your performance, your heat pump performance versus your resistance heat, because that's how we measure 1 kilowatt equals 3,400 BTUs of heat. So that's the input we're using to get the COP output of just how that economic balance point works around heat pumps. If we scroll down to just an example of winter peak, so this is, I believe, it was probably in 2021 where we had, I believe, the storm Uri. I could be wrong there, but we had Snowmageddon in Texas. Texas was just, and if everybody on here is from Texas, that was just a time to be alive. It was a complete week or maybe week and a half of snow, freezing temperatures. Texas just isn't, we understand now that Texas just wasn't prepared for that, looking back on some of this stuff. So moving forward, the chart that you see on the left is taking an example of a winter peak load or a typical winter peak load, and you can see the difference in performance or kilowatt usage between different sources of heat. So your top teal line is your resistance heat. Your more of your darker blue is your air source heat pump, which we are talking about. And then you have your air source heat pump with deep energy retrofits. The deep energy retrofits don't really attain to us here in Texas, but I want you to take a look at the outside air temperature. So you see the outside air temperature dropping and then coming back up on a typical day. And then I want you to look at the top teal and then in the middle there where your air source heat pump is. So looking at the kilowatt difference in what a resistance heat or an electric heat kit has to do versus what a air source heat pump has to obtain, it's a lot less energy usage. And if we shift this over to the right hand side, as far as looking at the maximum load shed requested during the storm that we had in 2021 is, we were, I think that's 20,000, I think that's in megawatts, that we needed to load shed in order to stay pretty much on track with keeping the grid alive. And so if you take that into an example where, if you take 11.2 million housing units and you have a certain amount of kilowatt savings, let's say 3.8 kilowatts, we could essentially, in that particular instance, avoided a grid outage if everybody, or not everybody, but a certain amount of people in certain major metros were to switch to some sort of air source heat pump, just given the fact that when we look at the COPs and what typical residential people have in their homes and look at the energy savings in kilowatts, we could do some simple math and say, if we did this, then this would occur. So it's more of a topic of discussion when it comes to on the demand side, where do we need to be plugged in instead of taking this kind of whack-a-mole type approach to demand response. And the whack-a-mole, I'll kind of get into this in a few slides, and you'll see some of the energy co-ops out there who have some of the smart home upgrades or the home energy programs that are out there are more of a band-aid for a much bigger problem. And if you want to do kind of some of on your own here, this is a cool little homework thing that you can do is on ASHRAE's website, you can actually go in and give a generalization of how much you could be saving in both energy and see your 5, 10, 15-year savings over time. And how this is calculated, this is a real world example. I believe this is my parents' house. So they have an older system that's probably 10 to 12 years old. And back then, the SEER rating was 13 probably on that system. And then if we go with the current tonnage there in the middle, keep it at 3 tons. But your minimum for minimum, meaning that if I just basically did a like for like unit in today's time, uh, I would only have a 13% savings per year. And as you can see, over the next 15 years, not a ton of savings. Obviously, it's going to be minimal year to year because that system's so old. But if we go in and we actually do minimum versus high efficiency, now we're looking at some real savings. So again, keeping the same older outdoor unit that was probably 13 SEER back then going in with the same 3 ton, but saying now we want to shoot for a 20 SEER rating. It's going to give you some type of an output depending on your zip code as potential savings per year. And now we're talking almost triple, if not quadruple, our savings over a 15-year time period. Again, that's on ASHRAE's website that you can go in. I believe it's under, it might be under the rebate or performance incentives that are out there, and you can calculate this out just given your zip code and what you pay in in kilowatts for cents in kilowatts where you're currently at. And if we look at the peak demands going back 2 or 3 years ago during the summer season in Texas, it's only increasing. It's only increasing, and it's going to continue to increase as we introduce more more housing into the market, as we introduce more home buyers that are able to afford homes into the market. So we have to find a perfect way to balance this out. And there's could be a lot of ways to do it, but there's also simpler ways to do this. And I think if you rewind about 5 or 8 years ago, there was this big push around home energy programs. And depending on how that energy co-op released these programs, really determined the outcome. I can tell you from my point of view that, yeah, the home energy program, I think, was a step in the right direction. However, it gave the utility company complete authority over what you were doing as far as your HVAC system in your house. So it caused a lot of confusion, especially with I'm just going to call them the boomers, right? So they caused a lot of confusion with people in that age range of 50 plus. They didn't quite understand what a smart thermostat was. Nobody was really going into the house and teaching these guys or gals how to use the smart home thermostat and how it worked in correlation with the program they just signed up for. So it created a lot of bad user experiences. The You had to sign up for it through your energy co-op. You would get either a Nest or somewhat of a co-op branded Wi-Fi thermostat that had the API logic in there, which gave the city the power to throttle up or throttle down your usage when it came to the peak load of time in that city. So you had a lot of confused people out there wondering, they're leaving the house at 74 degrees, but when they get back, it's 78. So they signed up for the home energy program. They had a bad experience, and then they got rid of it. They didn't like the way that the city was utilizing the thermostat to basically throttle what they were doing. And it's really a band-aid approach for a much bigger problem. So it created a lot of animosity when it came to some of the home energy programs. Now, in certain cities, I heard it working tremendously well because it was approached differently. There was actually classes given to the homeowners on how this would work. They were incentivized to do it. So things of that nature that could be approached differently, you might have a better outcome when it comes to those types of things. Now, the residential trend side of things is, I'm just going to go over a few key points here. Is major trends right now. There's a couple of them here, but solar panel. So solar has been kind of this growing segment of home energy conservation, home power storage. It's been a big deal, at least in the last probably 2 to 3 years, than it ever has been. And when we look at solar ready and Energy Star qualifications, is our systems are really good matches and marriages with solar power systems because of the amount of energy that we draw. Battery storage. Battery storage comes from solar panel generation. It can come from 2 or 3 different sources, but battery storage is becoming more popular. Heat pumps are becoming more popular. High efficiency washer and dryer when it comes to going all electric. Induction cooktops. I've looked into these. They're a little too expensive for my blood, but I know a couple of people who have them and they absolutely love them. LED lighting, weatherization of the home itself. If it's a existing home already, some of these home energy programs, in order to be incentivized to upgrade to any of these things, whether if it's a heat pump, water heater, or a heat pump, or solar panels, is that your house has to have some sort of weatherization score. So if we're taking a home that's 100 years old or even 50 years old, doesn't have the proper R value of window or insulation or roof, all of that has to be upgraded in order for the homeowner to see any incentive from upgrading any of the appliances to their home. So some of the weatherization side is a good thing. It can be a little confusing for the homeowner if it's not presented to them very well, but it also helps the fact that we are trying to build a more resilient grid without having to attach a bunch of window units to a 100-year-old home, or a 5-ton or a massively oversized unit to a home that needs it because it's very leaky. So a lot of the industry trends on the residential side are focused on moving homes that are in that leaky category to a more tightly built envelope. And then moving forward with that is net zero and net positive. Now, this is sort of a niche segment right now, but it is growing. So when you see a net zero home, just think of the home as using the energy that it puts out. So a home that produces as much energy as it uses is a net zero home. A net positive home is a home that produces more energy than it needs. So it almost essentially gives back to the grid. And where we see a lot of net positive is homes that uh, are in that FIAS range, or they're in the green certified buildings range. Net positive, it's a smaller segment of net zero, or when we talk about the green initiative buildings. I would highly encourage y'all, if y'all wanted to know more about the different segments or ratings of homes, the NAHB, or National Association of Home Builders, has a really good interactive site that you can go to and learn how to even make your own home net positive or net zero. So this is also another growing segment on the residential side. When we look at energy upgrades, or when someone is looking at building a home, even this is becoming a big topic of discussion. Because as we look as normal homeowners, we're adding a bunch of stuff to our houses now. We're adding pool heaters, jacuzzis. We're adding electric car chargers. All of this stuff is continuing to add more to our load. So if we can take some of the bigger appliances, not just our HVAC system, but our HVAC system consumes probably 60%, if not 75% of our total energy consumption in our home today, and implement something that does have less energy usage attached to it, then we can maybe start shifting around or load shedding some of that other energy elsewhere in the house, or give it back to the grid where we weren't using it before. When we did a couple surveys, probably about 2 or 3 years ago, a lot of millennials, because now millennials are in that home buying process, or they are the biggest segment of home buyers currently. They're excited about the HVAC, the solar, the electric vehicles, the heat pumps, because this is a generation that is kind of in tune with what's happening, either at the DOE level, at the government level, at the incentive level. We're always trying to look for what's going to make their household run more efficiently and cheaper so they can save that money. I like to make this analogy is my dad always tells me he bought his first home for $38,000 back in the 60s. And that house was 1,200 square foot. It had good bones, yada, yada, yada. Now you can't even buy a car for $38,000, let alone a house. So this is what millennials are gearing towards, since they are the biggest segment of home buyers. And when we look at the heat pump sales versus gas furnace sales in 2022, and they've done this every year since 2022, is we have actually surpassed on the heat pump side the number of furnace sales versus heat pump sales. So growing trend, and we do believe it is due to the trend of who's buying homes, who is retrofitting homes, who is looking for the incentives to install more energy efficient appliances. And when you look at Energy Star, or even manufacturers who look to meet Energy Star standards or ASHRAE standards, there's a lot more energy efficiency appliances out there today than there was probably 2 or 3 years ago. And then some of the things that prevent people from considering a heat pump is, the top three things on there, right? Cost of installing, don't see the need. and ability to heat my home. So you can see that the ability to heat my home is still one of the major concerns. And I mentioned earlier that, the contractors that were out there, 10, 15, 20 years ago, may still be receiving the same message that heat pumps maybe just don't work in cold climate, which we know that they do for a fact. And some people don't see the need, and then, but also cost of installing. So I kind of want to debunk some of these. And a lot of people, the reason why they don't see the need is because they can't really make the justification of, my cost of ownership versus incentives to go behind it. So if you want to go to MitsubishiComfort.com, you can go to our rebate center and you can type in your zip code and it'll show you what rebates are available per system. So this makes it somewhat easier for somebody like myself to go in and maybe justify the cost of replacing before burnout my older system versus a heat pump. Now, I think we'll all kind of get on the same page as far as cost comparisons go towards the end of this presentation, because with the recent industry changes, tariffs, government and political atmospheres, everything's gone up in price in the last 3 or 4 years, and it still continues to go up. So the cost will only justify or the value will only justify the cost. So that's a big part of our job too on my end, is to make sure that contractors are in tune with what their homeowners actually need and how to present them with the best information possible for them to make a good judgment on what they want to do in their home. Tax credits, the 25C tax credits are still around. This has been a big trend for a couple of years now. So at the end of the year, take it to your CPA. You can get up to a $2,000 tax incentive when it comes to upgrading appliances in your home. Same thing on the 45L side for builders and contractors, anywhere from $2,500 to $5,000 for zero energy ready homes in the single family, multifamily, and then that $500 per unit or $1,000 per unit if you're energy ready. And I have some different examples of this at the very end. There is a personal testimony in here from my counterpart Garrett, who is in Austin. And about a year ago, he changed out, forget how many years it was probably maybe 8+ years old, his 4-ton AC unit with resistance heat. So he had a just a straight cool unit, was not a heat pump, so it would cool in the summertime. And then when it came to the heating side, his house was strictly resistance heat. And this is very popular in the South because, in the South, when heat pumps were introduced, they didn't get a good rap. So a lot of people will tend to go the straight cool way in most cases because, for winter peak loads, they envision that they're not going to be there very long. But when you look at the amount of amperage that you have to have, is he had to have a 60 amp outside with a 60 amp inside for the heat kit and another 40 amps inside for his air handler. So all in all, you have 160 amp service just providing for the HVAC system. When you look at what he did afterwards, he did a 3.5-ton variable speed heat pump, which only required a 30 amp breaker outside. And he did a single zone for his office, which only required a 15 amp breaker. So when you look at the Mitsubishi side, another benefit is the indoor units are powered by the outdoor units. So you don't need a service box on the inside to power any additional inside units like you would need on the old Tempstar. So essentially, he went from 160 amp service to 45 amps, and then he was able to disperse, that extra 125 amps elsewhere. Now he does have 2 electric cars, so he was able to use the amperage that he didn't use for the AC system and throw it to his electric cars. But essentially, he's not using 160 amps more anymore to heat and cool his house. So when you look at cost comparisons, your average install price since 2020, right? This was COVID, it increased by 40%. So if if you remember, supply chain disruptions were and raw material shortages were a big one back in 2020 because a lot of homeowners were staying home. They were investing in their home's equity. They were doing renovations, upgrading their HVAC because they were home more often. And ever since 2020, 75% increase in average installation prices. So on a national average, you're going to see $12,500. I can tell you in South Texas, it's going to range anywhere from, if you're going to go with just the bottom of the barrel system, you probably can't get a bottom of the barrel system anymore for less than 10 grand. And if you're going to go with a top of the line system, you're probably going to pay $22,000 plus. So as time progresses, we are probably going to see more and more of this technology increase in price, where we need to see incentives combat that. So, incentivizing customers like they do on the West Coast or East Coast to adopt this technology more is going to probably be the key for the next couple of years. So some of the cost factors that are out there are obviously brand, right? What brand are you going to buy? You can almost relay this to the automobile industry. Are you going to buy a Kia or are you going to buy a Cadillac? Efficiency level, so SEER rating, EER, Energy Star, tax incentives, like what qualifies for that? Material cost. Every manufacturer buys their materials from all over the place. So that's going to be included in your cost. Your supply chain disruptions, which we've seemed like we've been going through ever since COVID, that's going to be a cost factor. And new regulations. So new regulations meaning, our A2L transition that we're currently doing from, 410A equipment to R32 or 454B. Those will also have an impact on cost. The one thing I want to tell you is a lot of times when I'm presented with, hey, your system is, a couple $1,000s more than the system I got quoted yesterday. These are the questions that I like to ask. Is it apples to apples? Is it the same type of technology? Is it the same support structure you're going to get? The functionality and efficiency is the same energy cost or running cost. Did you calculate your 5, 10, 15-year cost of ownership or your savings? Are there tax credits and rebates available for that system? These are all questions that homeowners should be asking themselves when they look at going from a Kia to a Cadillac, because I think the upfront cost is somewhat marginally more, obviously, than going with your 14, 15, 16 SEER single stage systems. The same can be said in the commercial world. Are you going to go with a rooftop unit, or are you going to go with a Mitsubishi air source heat pump with two dual 8.5-ton air handlers inside that take a lot less energy to function? So all of those go into cost comparisons, and sort of the why a residential person or a homeowner should look at going towards heat pumps is they have to become educated on technology. That falls solely on their responsibility or the responsibility of the contractor. So if they are in tune with what is the reasoning behind the technology and actually how it works and how it differentiates itself from your single stage or your dual stage systems out there, that could be a big you know arrow in your quiver to figure out why a residential person may pull the trigger on doing a heat pump. Incentives and rebates. So incentives and rebates, I'll preach this all day long, is I think, especially in Texas, this is where we lack. We don't incentivize and we don't have high-end rebates to push this type of technology to help reduce the cost of ownership or cost to install. I'm a firm believer that if we are wanting to build a more resilient grid, take more load off the grid, however you want to word it, we need to be able to incentivize homeowners to basically afford the technology in order to do that. Reduce utility consumption, hand in hand with incentives and rebates. Overall owner experience. So this goes back to, what type of experience are they going to get from installation to user friendliness? more comfortable spaces. So if we're doing multi-zone, we're obviously doing a better job at air quality because if you're doing multi-zone per room, you are now filtering the air that is in every single room due to every single return that's in that room. If you look at a conventional system where you might have two returns in a 2,000 square foot home, you're really only filtering the air within the vicinity of those returns. So you can potentially increase your air quality, increase the comfortability of that space, turn on or off different zones, and then equipment matches the needs of the space. So what I mean by that is, what type of space are you working with? Is it a space that's not going to be used? Is it a space that you're going to stick your mother-in-law in? Those types of things. Those are all types of things that a homeowner should look at when making a big purchase like this because it is the number one appliance in the home that will use or utilize the most energy in that space. When we look at some of the commercial trends, so moving away from some of the residential stuff, historically speaking, some of the older technology that is still around today that is much more advanced than it was is, if you're talking about heating a commercial space, a lot of that was done by boilers, whether if they were oil or natural gas fired. A boiler would be a steam plant where you would utilize combustion to heat hot water, then send it through the rest, send it through the rest of the building. That technology still exists today. Uh, Probably the most popular one that I deal with, though, are RTUs or rooftop units. So these are these big, gaudy looking things on top of roofs that require probably, I don't know, 120 amp service to operate. And you can get them from anywhere from 5 tons to probably up to 35 tons. So these are probably the most popular way of heating and cooling commercial spaces. And even when we look at the condenser farms, when it comes to multifamily, I see this all the time when I'm in a high-rise hotel is I continue to look down at this and say, oh my God, every single one of those has probably a 30 or 40 amp breaker attached to them. And those line sets are probably hundreds of feet long, losing a ton of capacity going from the condenser to the indoor air handler, and those systems are probably running all day long because you can't get the performance out of them. They're not rated to perform with longer line sets than what they're currently rated for on submittals. So historically speaking, this is how always on the commercial side or multifamily side, this is how things have been heated and cooled for many, many years. So when we look at what would be some of the reasoning behind moving towards more of a heat pump style or air source or even air to water heat pump is, you're going to look at lower operating cost for a commercial developer. And the building that's in this picture, if anybody's familiar with this is the Credit Human building in San Antonio, Texas. And the Credit Human building was a ground up project that the commercial developer said that he wanted to hit certain goals when it came to the LEED qualifications, when it came to solar production, water recycle, elimination of combustion gas. He didn't want any of that involved in this building. And so when he went in and did all of the design and gathered all the manufacturers to come on board with this, he attained what he wanted to do, but that was the vision of that particular owner or developer, and not everybody is centered that way. So when you look at the reduced carbon emissions or carbon neutral, is there's no fossil fuel combustion inside of that building. Cost effectiveness. So this goes back to some of the IECC code compliance, and when it comes to demand response and occupancy setback, you don't really get that with a rooftop unit or a boiler or a chiller. The more times that you can sense people in or out of an area and be able to set back temperature and not have a system run or turn off, that's a major advantage. Improved air quality and comfort. So This is going to be, floor by floor zones. It's going to be floor by floor temperature. If you're not using a certain floor or a certain floor is vacant, there's no reason for that floor to even be calling for cooling or heating. The government incentives behind this. So the government incentives, whether if it's the LEED process or if it's the Green Building Initiative, there's a lot of different tax deductions and incentives out there for a developer to go towards that route. And, in the end or over time, it makes sense to get those building certifications. And then you're able to drive the sustainability message for other developers in the area who are looking at doing something similar to this. But I would say that, you have to be aligned with the right manufacturers. And then not even like talking about HVAC, but what lighting you're going to use, what solar company, what panels are you going to use, what type of water regeneration are you going to use, or water recycling plants. Like all of that has to come together in order for any developer to take advantages of those programs. So some examples of this that are out there today currently is if anybody's familiar with the Hotel Marcel, this used to be the old Pirelli tire company building. And it was essentially renovated into, I believe it's a Marriott Platinum certified building now. So it's 100% electric. The HVAC is done by our domestic air to water heat pumps. So domestic hot water, the heating side and cooling side is all done on a water sourced basis. And it has all of these different certifications. And the developer, very similar style as the Credit Human, is they wanted to do something different. They wanted to achieve the LEED Platinum certification, Passive House certified, which is just a rigorous uh, lengthwise of testing and making sure that you're within regulation of passive house requirements, and then being U.S. Green Building certified. All of these things have tax deductions and incentives attached to this in order for them to do this, but also it creates a really cool way of rebranding a very unique looking building and attracting more of a clientele, but also it's hospitality. So you're creating somewhat of a better environment, a better customer experience when utilizing these types of technologies and going for these types of certifications. Another example is our Kipton Grand Roatan. So we have an international business unit that will go to the Dominican, Mexico, any of these areas, and they will work with contractors in the local area. And I will say that a majority of these contractors, they're craftsmen. They own the ability to go into a new construction build like this and own the process from installation to customer experience. And in this particular instance, they had very little room to work with when it came to where were they going to mount units? How quiet are they going to be? They are known for having some of the best customer experience and reviews as a hotel agency. So this was a very unique job for us. This one was just started up probably a couple of months ago. And so this one was kind of our flagship for some of the tropical climates and environments that our stuff does and can and works very effectively and efficiently in a tropical environment. Now, when we look at the elimination or renovation of a particular style is the removal of chill water or removal of central steam plants. So this happened at the Weber State University College. So the engineering department approached us several years ago. They've been renovating for a couple of years now. They wanted to look at the reduction or their essentially the reduction of the combustion of fossil fuels on campus. And so they started with, where do they get their hot water? Where do they get their HVAC? Where do they get their heating from? So they've completely transitioned from being a fossil burning campus to utilizing our air to water, heat pumps for hot water sources. So they use it to heat and cool the entire campus, and it's become a big focal point for us moving forward when it comes to what are we going to, what's our strategy behind the transitioning of college campuses. So all of those things in conjunction is, there's going to be best practices when it comes to installation, homeowner activities and things of that nature. But these are all things that normal contractors should know about is manual J, manual S, to the ASHRAE design conditions, what's the location, orientation, all this stuff that is meant to keep contractors out of trouble, engineers out of trouble, and provide a great experience for the homeowner. These are all the proper processes in place that contractors need to accomplish in order to do so. So proper loads, they'll avoid oversizing and undersizing of equipment, creating a more or a better comfortable environment for the end user instead of going oversized or undersized. Your duct design is also a key part of this. Now, not all of Mitsubishi systems utilize ductwork, right? There are some ductless capabilities, but looking at these are all real life pictures that I've taken in the field, and this is just unfortunately what you see in a lot of end users' homes or spaces. And so when we look at the amount of load that could be potentially added due to ductwork, it could be up to 25%. So moving away from ductwork in a sense where we can utilize ceiling cassettes or high wall units, minimize the amount of ductwork and centralize different zones to have the zoning capability, reduce the amount of ductwork. Those are all different scenarios you can play around with. And then dehumidification, being in the South, this is something that we have to combat every day of the week. And dehumidification is a byproduct of air conditioning. When you go and install that unit, it is made to condition the space, not dehumidify it. So it's nice to have dehumidification if you can have it in one big package, but that's not the case. So in order to have the best of both worlds, we will always be the advocates for, in order to provide the best user experience possible, utilize a dehumidifier when possible, an ERV when possible. If it makes sense, do it. Also, protection for your homes against power outages, power surges, or underpower. This is experienced more often than not on the coastal plains area. So the coastal regions are known for having a lot of dirty power. This could be due to weather, wind, hurricanes. Houston is notorious for this, even like rolling blackouts. What we don't want is to have a surge of power or an undersurge of power servicing the systems, because we could see potential failures of inverter boards, compressors. So a good practice is to always have some sort of voltage management attached to each outdoor unit. This could be in the form of just a small Dytech Cool Guard, which looks like this, or a much larger Dytech device, which looks more like a service panel if you're, more residentially focused. So some tips for moving forward is utilize your resources, right? I'm one big resource. Spear is also one big resource. Diamond System Builder also keeps people out of trouble. It keeps designers out of trouble. The Diamond System Builder will allow you to build small systems, large systems, high-rise systems, custom home systems without letting you make a mistake. Our MPro website, so mpro.com or mitsubishipro.com, we have all of our data. We have all of our, submittal packages, installation manuals, things of that nature. All of that is available to you at mitsubishipro.com. Also, another big one for me on my end is the training of contractors. We have, I think, 18 training facilities across the country, with 2 of those being in Texas, one in Dallas and one in Houston. So if you are an architect or an engineer who wants to get your hands or on some of this learning material, feel free to reach out to me or Randy or anybody at Spear to go through one of these classes with contractors to see what they kind of go through, to see what type of testing or knowledge or product knowledge is presented in these classes because everybody can pick up on certain things during these types of classes. I'm going to wrap this up with the industry changes that we're currently going through, and then I'll open it for some Q&A. All of this to say is the refrigerant transition that we have been making is from 410A to 454B is our going to be our refrigerant of choice on the residential side, R32 being the refrigerant of choice on the commercial side. All trying to attain a certain GWP mark. So right now the GWP mark is below, I believe, 700. So everybody's having to make that transition. So we are already through our transitional phase. It's just a matter of getting our products into consumers' hands. So that's being taken care of on the back end behind the curtains. Some of the key takeaways though here is, if anything, wanted you to understand that not all heat pumps are equal or the same. And we do have all climate or cold climate ready heat pumps available and at the ready with hyperheat. The homeowner perception happens at the kitchen table. This is more so on the contractor end to be more in tune with what the consumers may want and you having the product knowledge in order to sell value over price. And then the last thing here is take into consideration your load calculations, your manual S, your manual J. All of those things will keep you out of trouble. So I don't want to go over time. I know we might have a couple of questions in the chat. Randy, if you want to spout those out, or if anybody wants to ask questions, feel free.
Yeah, I don't see anything right now. That now's the time to post some questions in the chat or the Q&A. We can go through it. But I did have just a couple of comments. So fantastic information, Sean. I really appreciate it. I've learned a lot from, I've gone through others with Spear and some of the stuff that we've done. The Mitsubishi stuff, technology wise, I haven't really had a lot to do with that, and I learned a lot today. I don't know. I think I might have met you or someone else at Mitsubishi. I know I met Garrett. We did a Spear and I believe Seco put the first one on in Austin. We did a training like you showed the pictures of. It wasn't really a hands-on with the equipment, but it's more of a presentation discussion. We also did one in Houston. We are planning on one in Dallas. We'll get that date out to you probably later in the year. Just look for that in our newsletters, and you can register for that or have one of your guys or technicians to register for that. But just a couple of things. Do you know what's the average in your equipment, your technology? What's the average square foot per ton that you guys are working in now? I know it has a lot of
that's
variables to it, but roughly.
that's an open-ended question. The industry standard, I think that is still tossed around is I think it's like 400 square foot per cooling or per ton or whatever it is. The I've seen a lot of the like net zero or net positive homes or even your FIAS uh, type style builds. I mean, they're probably, gosh, 1,600 to 1,800 square foot per cooling ton, and that's awesome. It's great
Yeah.
to see. It's great to see that. But there's a lot of, like I said, still a lot of first gen, second gen contractors out there who are still abiding by some of the older norms that get them in trouble.
Oh, of course. Yeah, if you're a plan reviewer out here on the call on the webinar today, I mean, technically, I mean, 400 to 500 was the rule of thumb in the old days, and now we're looking at 7 to 900 square feet. So if you're doing a plan review, just look for something on the higher end of that. But as we keep reminding, manual J and S's are still required per IECC. That's been in the book for quite some time. I know there's a lot of cities that I visit and talk to that they collect a manual J but not the S. The S is the other side of the equation where J doesn't do anything but give you the load, S matches the equipment, which is very, very important when you're looking as if it's the right size. But also manual D is coming in the energy code in the near future, right around the corner. So it'll also have, you'll need a duct design as well to review and plan review. So that's something that Spear can help with, and then experts like Sean today, and we can get people on the line here to do some run throughs on how to verify manual JNS. We've done that before in the past, but it still continues to be questions to me through my technical assistance number through Seco. I get phone calls and emails about how do I tell when it's wrong, or how do I tell when it's not right. So we still have questions with that, but a lot of good information you threw out there. I'm going to look into that Cool Guard 2. I've got a staged equipment with variable speed furnace, but I don't have it protected, so that kind of gives me the heebie-jeebies. And then the ducks picture that the ducks pictures of the ducks in the attic. I mean, that's things of nightmares for me because I see that all the time. That stuff's very important to discuss. But also wanted to point out like that Credit Human building and then the Hotel Marcel. If you're on the call and you're a plan reviewer or you're a building official, if a project like that's going in and you've got a builder or a developer that is really in tune with green stuff, I mean, I can only recommend highly that you get more involved in the project and meet the design team, talk about why they're doing it and how they're doing it, things that they're saving and things that are making a difference to the building, and how things connect as a system. That can actually show you that when you put your head to it and you design it correctly, that things can be achieved. And then you get these other developers that basically scream and yell about not being able to do certain things that are just basic code required. There are others out there that take it to the extreme, and you can tell that it is achievable for that part of it. So always be part of that. And then, of course, if you're an HVAC guy on here, always try to be part of the design stage in a project like that. It's just, it's things that you can learn and you can put that information to use in future projects. So, Sean, I
Yeah,
don't see. Go
no,
ahead.
you're good. You're good. The manual S question has come up a lot in the past, and how do I know if I'm doing my manual S correctly? And all it is just equipment selection. So if you have your manual J load and you believe it's accurate, you can utilize Diamond System Builder on our end, which will give you the performance output per ASHRAE or AHRI parameters that you give it, and it'll tell you exactly what that system will do performance wise in both sensible and latent cooling capacity and heating capacity.
Yeah.
So very helpful.
Yes, absolutely. Well, great information, Sean. Again, I really, really appreciate it. I know we'll be in touch in future webinars and in-person training as well for Spear. Can't thank you enough for taking your time to do this for us. We're still continuing the series. I think we'll have another technology in the heat pump world that we'll be doing another webinar in the future. But join us on our next webinar that we'll do. I'm going to attempt, I've done a lot of research and everything to try to put together at least a 30 or 45-minute high-level overview of this new A2L refrigerant changes and what's happening. I get a lot of building officials asking the safety of it, the flammability. We're just going to kind of run through what I've now been able to find for information online. So there's some lesson learned you can see on the screen. I've kind of put together a bonus inspection checklist for building officials. So just a kind of again, high level where you can check off the boxes to say that you've done your due diligence when you're reviewing these new refrigerants. So, Sean, last thing I want to ask you, I know you spoke about it a little bit, but keep seeing highlighted headlines all over talking about how bad this shortage is with 454B material and equipment. Is that true for most markets and most companies across the board, or is that something specific to an industry or a market?
Well, so the 454 is manufactured by Honeywell, and Honeywell has had some issues getting the raw materials for the drum. The drum is a new style of drum. It's a 20-pound drum instead of a 25-pound drum. So the refrigerant itself is not scarce. The raw materials and making the drum is it's scarce and it's on tariff right now.
Got it.
So yes, it is somewhat true. However, it's extremely temporary. Some of the intel that we have gotten as a manufacturer, and as well as many other ones that are using R454, Temporary meaning, this could be something that lasts maybe up to the next 6 to 8 weeks in some instances. So we'll start seeing some of that kind of wean off. When you're looking at some of the pre-charge limits that are coming out of the box, Mitsubishi is the leader in what's coming out of the box, meaning, if you wanted to do a ducted unit, we do have line sets up to starting at 30 foot that range up to 100 feet of pre-charge line set. So it hasn't really affected our product line due to the proactiveness we've had. We've always had that kind of uh, benefit with utilizing our product. So yes, it's temporary pain. It won't be around for much longer, but it is definitely a topic of discussion.
Great. And of course, last time we saw, and you mentioned it too, in COVID, when we had equipment shortages, I was still in the field doing third-party energy inspections, and it just, you could count on, four or five different hands about how many times during the week people would say, well, I just can't get the 3.5 ton, I'm just going to put a three, or I can't get the 3.5 ton, I'm just going to put a four. They want to
Yep.
continue construction, but that makes a major change in the
Yep.
design of the building and the usage of electricity in the building. So just be sure, and I'm glad you're saying that's temporary and a short supply shortage, but I hope it doesn't run into those ripples again because that became a problem.
Yeah, we've
So
been in we've been in much worse situations. I'll put it that way.
exactly. Well, guys, thanks again. This is my contact information. Feel free to reach out to me if you have any questions, thoughts, concerns. You will receive a survey with this webinar, and after you fill that out and and send it back, you will get CEU certificate for that for attending. Thanks again for being here. As always, connect with us. This is our main number, our website. We're on Blue Sky now. We're also on LinkedIn as well as X, and that's our handles that you've got there. So thanks again, everybody. Everybody have a safe and great week. And Sean, appreciate it again for the information. I thank you wholeheartedly because I learned a lot today from Mitsubishi Technology. Thank you.
Not a problem. Thank you.